Hello, my name is Gary Millette, and this is ELE-110 Electronics for Technicians 1. It's a fall of 2020. This is topic 9B, meters and wire size. So we've talked a little bit about this stuff before, but I'm going to go over it again. First slide here is called meters. One of the oldest and most common tools for to deal with electric circuits is known as a meter. Historically, the galvanometer was around during 1825, which is close to 200 years ago, and Ohm used such a device to do his famous experiments that we now know as Ohm's law. For a long time, meters were analog in nature, with the device consisting of a rotatable needle. The rotatable needle would respond to a current flowing through the meter by deflection of the needle and its position in relation to the meter scale display. So there was usually a coil of wire wound around this some type of magnetic material, and again we'd pass a current through that wire. It would cause the coil to make a magnetic field, and there was another magnet, and it would take and respond to maybe opposition, that is a repulsive force or so forth, to rotate the needle. Usually the needles were set in such a way that they were on some type of low friction rotatable type of mount. The Sen gauge material goes into a lot of detail about analog meters, and you should go over that material online. However, in our view, the era of analog meters is over, and there's no real reason to spend time on an outdated technology other than to be aware of how to use the technology if you're forced to do so for some reason. Today we use digital meter technology. This technology is both mature, reliable, and in many times very inexpensive. So here's an old analog meter example. You see the needle there with the red tip on the end and the scale, and this looks like a VU meter, volume meter, maybe on something like a tape recorder or something from many years ago, piece of equipment. And it turns out that it's hard to notice, but there's actually a set screw there right where the needle rotates around that locus of points there. And if the needle didn't go back to zero, you could adjust it so it was on zero when there was no input. So here's a couple of portable analog meters, well, just one. The older portable analog multimeter, the green one, the B&K Precision, is shown here with its modern counterpart, a DMM, we call them digital multimeter. And that's the one on the right-hand side. It's also a B&K type of meter. And you see a digital display as opposed to the numerous scales on the one on the left. Not easy to read. So the scales of an analog meter are not easy to read. First, you must determine the correct scale that you will need to read from. Then you need to make the reading. Digital voltmeters are auto-ranging and just show you the reading. So everything's automatic. Notice with this analog meter, you have to select the scale, which means you have to select what when I say select the scale, you move that switch to select what the full scale range will be. Then you have to figure out what the scale is that you're reading off of. So digital meters. Today, digital meter technology is mature and furthermore lends itself to data acquisition since the reading has already been encoded as a digital word. So many of our meters today will actually take and store the samples of what they're reading. And you can either get that information wirelessly, or you can somehow put some type of cable into the meter to get that information. The analog to digital conversion technology has been around for decades and is fast, reliable, and accurate. Today, one can purchase a low-cost digital multimeter for use around the home that has a great deal of functionality and a high degree of accuracy, and they're very inexpensive. So here's this is a fluke meter, and you can see that this is again an advertisement probably for a fluke meter. The one in the middle there, probably in its prime, that was probably about 150 bucks for that meter. Today it might be a little bit less. So that brings us to wires or conductors, and of course they are a fundamental component in anything electronics. Wires have existed for over 200 years. Recall the telegraph was invented in 1836. coming on the 200th anniversary of that. The early telephone systems used iron wires. That was the easiest to make years ago. Today, most wires copper or copper coated. And in a circuit, a wire is considered to be a perfect conductor with zero resistance. Early resistors were constructed from lengths of wire, most likely iron wire as opposed to copper wire. This is a picture here on the right-hand side. This very old picture depicts New York City. In the late 1800s, there were many telephone and electrical wires. They were all above ground. They were eventually buried underground with the subway system when the subway system was put into operation. And what they would do is just, you see the cross members, if they need to put more wires up, they put more cross members on the poles. Wire characteristics, the size of wire is its basic characteristic, and of course what it's made from. Wires vary in diameter but conform to the standard gauge sizes called the American wire gauge, or AWG. The larger the AWG number, smaller or thinner the wire. That seems backwards, but that's the way it is. Wire sizes are given in terms of cross-sectional area. This measure is called the circular mill. So here's a AWG table. American wire gauge sizes for solid round copper. And you see the numbers 1 through 40, you probably would grab your eye first, but then you see 0, 00, 000, and 4 zeros. It turns out they want to make larger size wires, so they made single-aught, double-aught, triple-aught, and quad-aught, they call it, wire, which was bigger. The area in circular mills is given by the equation A equals D squared, where D is a diameter. You might notice that they show the wire number, the area in circular mills, and the number of ohms per 1,000 feet at 20 degrees. So size 40 wire, which is thinner than a human hair, 1,000 feet of that wire is 1,049 ohms. Whereas size 0 wire, 1,000 feet of that is about 1/10 of an ohm. Now, the two wires that are probably most commonly known are size 12 and 14 because they're used in resonance wiring, which we'll get to in a couple minutes. So, wire resistance, any wire except a superconductor will have resistance. The resistance is proportional to length, the wire's resistivity, and inversely proportional to its cross-sectional area. The equation for that is R is equal to rho, which is the resistivity, times L, the length, divided by A, the area. So here's a wire resistance example. It says find the resistance of 100 feet of copper wire with a cross-sectional area of 110.1 circular mils. The resistivity of copper is 10.37 circular mil ohms per foot. You do the calculation, it turns out to be 1.28 ohms. So again, a foot of copper wire is very low resistance. What about grounds? Ground is a reference point in the circuit and it has a potential of 0 volts. Earth ground is commonly used by the utilities, electric, telecommunications, and so forth. Electronic equipment often uses a chassis ground, which may or may not be connected to earth ground. A car uses a chassis ground. Ground is an important safety consideration. Here are the symbols for ground. A is the more traditional one. B and C are newer symbols. Grounds are a common point in a circuit. So the figure 238 here shows a simple circuit with ground connections. So the ground symbols at the bottom of the battery and the light, it turns out that is, say, maybe the chassis, and there's a connection between those two, so you have a complete circuit. This picture shows residential outlet wiring, and you should be aware of this because there's some differences between what we do in the electronics lab compared to your home or apartment. Note that unlike electrical circuit conventions, the hot lead is black and the neutral or ground lead is white in AC power wiring in a home. The black is ground and red is hot in our labs and also for cars. A 15 amp circuit will use 14 gauge wire while a 20 amp circuit uses 12 gauge. So this shows an outlet box. Normally you would take and run power to it, say 2-wire Romex with a ground. They call that 12-2, actually 3 wires in it. Notice the black wire comes out, goes to the outlets, and it goes to the short slotted outlets. And then the white wire comes out and it goes to the long slotted outlets. So in a home or residence, the outlets, the ground wire or neutral wire is supposed to be the long slot. The short slot is the hot lead. And the green or ground wire gets connected to the box as well as to the ground of the outlets. Here's a little more about how the breaker box is wired. So the power comes into the house or apartment. You can have 240 volt circuits. That shows a 60 amp sub panel up top where there's some 6-2 wire. 6-2 would be 6 gauge with 2 conductors and a ground. Then there's the orange wire that goes to the 240 volt electric water heater. So 240 volt circuits supply more power. That uses 10-2 wire. All the outlets are 120 volt circuits, which use 12-2 wire for a 20 amp circuit and 14-2 wire for a 15 amp circuit. So again, it goes to the outlets, goes to switches, boxes for lights. Shows down below some power vent water heater, which might plug in. Dedicated outlet for the microwave. I don't think you need that anymore. But nevertheless, this is just a pictorial view of how breaker boxes work in homes and apartments.